Yoshiaki ISHDA from Hokkaido University will deliver a presentation titled The Levee Failures at the Confluence of the Satsunai River and the Totobetsu River. First, I will explain the background to this study. The 2016 Hokkaido heavy rainfall was the heaviest in observation history, and unprecedented disastrous floods occurred in many areas of Hokkaido. During these floods, it was found that an approximately 200-meter section of the left bank levee of the Satsunai River failed, and an approximately 300-meter section of the continuous levee on the right bank of the Totobetsu River failed. In the survey after the flood, it was found that the water from the failed location at the upstream side returned to flow into the Satsunai River at the levee failure location of the downstream side. In conducting management of floodplains of rivers with rapid flows, understanding the flow characteristics in the floodplains and damage characteristics of floods occurring in such rivers is important. Therefore, in this study, investigation of the characteristics of the two levee failures and damage by flood flows at two locations on the rivers with rapid flow was conducted. In 2016, 3 typhoons passed over Hokkaido during the 1 week from August the 17th to the 23rd. After those 3 typhoons, Typhoon Lion Rock approached Hokkaido on August the 30th, after rainfall brought by a stationary front on the 29th. During that time, eastern Hokkaido in particular had heavy rainfall. The accumulated rainfall measured at the Totobetsu River Upper Reach Observation Station and that measured at the Kushinai Observation Station for the period from August the 29th to the 31st were the highest rainfalls in their observation history. This shows the animated 3D rainfall distribution seen from a point over the Pacific Ocean at the time of the 4th typhoon. This figure shows, from the left panel, a landform classification map for flood control. This photo was taken in 1959, before the levees were connected. At center is a photo taken shortly before the flood. The next one was taken immediately after the flooding. The one at the right end shows the area after the emergency restoration work. This video footage of levee failure at the downstream side of the river was taken by a CCTV. The structure at the center is a sluiceway, and the flat areas seen in the front are the panels for solar electricity generation. A survey was done for the traces of overtopping flow and the datum high water level at the locations near the levee failure at the upstream side of the river. No trace of overtopping flow was found at either of the levee failure sites at the upstream and downstream locations. It was found, however, that the datum high water levels were lower than the levee crowns. Therefore, the major factor for the levee failures at these locations is thought to be a lateral erosion associated with the movement of the main channel. This photo was taken by using a UAV immediately after the flooding. At the levee failure location, the main watercourse has shifted greatly toward the right bank, and the width of the sandbar became as wide as the length of the area between the two levees, which was 180 meters. It It is thought that this development of the sandbar was a factor that caused the lateral erosion and greatly affected the occurrence of the flooding. In the survey done for the levee failure location of the downstream side of the river, it was found that the traces of the DHWL were about the same height as the elevation of the levee crown, and that the levee crown had traces of overtopping flows. The overtopping from the inside to the outside of the levee was witnessed at about midnight, or 12 a.m., on August the 31st. From the conditions at the levee failure site of the downstream side of the river, it was thought that the levee failed because of the overtopping flow from the inside to the outside of the levee. The flood water flowed out of the river into the area inside the levee once, and then flowed back to the river, overtopping the levee at the downstream location. Main damages at the downstream areas were washout of a warehouse and large-scale erosion of the levee foundation. It is thought that the speed of the water flows was particularly high at these two locations. To examine the series of the flooding event, a numerical analysis of the event was conducted. A planar two-dimensional riverbed evolution calculation was done by treating the river channel, floodplain, and levee as one movable bed. For this calculation, iRIC D2 was used, and reproduction of the levee erosion was also done. For the topographic data, the laser beam profiler, or LP, data measured in 2006 were used. For the discharge hydrograph of the Totobetsu River, the one estimated by using the storage function method was used because the data for the Totobetsu River was missing at 3 p.m. and after on August the 30th. The estimated discharge of the Totobetsu River is set as 1,555 cubic meters per second, which is close to the design peak high water discharge of 1,700 cubic meters per second. This shows the animated analysis result. This shows the levee failure at the upstream location. This shows the levee failure at the upstream location. These show the simulated time series changes in the water depth. One shows the river conditions before the start of inundation. Two shows the river condition when the inundation started. The process from the lateral erosion of the levee and the following washout of the levee and to the occurrence of inundation is reproduced. The inundation started about 3.5 hours before the peak discharge. 3 shows the condition when the inundation flow filled the area inside the levee and started to overtop the levee at the downstream location. The time reported by the witness and the simulation result differ by about 30 minutes. However, the calculation result is thought to have reproduced the inundation fairly well. 4 shows the condition at the occurrence of levee erosion by the overtopping flow from the inside of the levee at the downstream location, or at the confluence. 5 shows the condition at the peak discharge. From this, it was found that erosion was progressing at a different location from the location where the overtopping started. 6 shows the condition of the area after discharge decrease in the later period of the flooding. These show the simulated time series changes in the water flow velocity. These show the simulated time series changes in the ground elevation. These are the conclusions. The main factor that contributed to the failure on the